Good afternoon, class. So today we'll move along into file system implementation. Today we'll look at file system structure, file system implementation, and directory implementation. And for your continued enjoyment, here are the chapter objectives. So I'll assume we all know what a file is. The file system resides permanently on secondary storage, which is essentially everything other than primary storage, RAM. But portions of the file system are brought into primary memory to speed access, in this case, and for modification of the of files and file metadata. So you can think of primary memory as a cache. Um, Data is transferred. On the disk, data is typically stored in 512 byte sectors, but the file system to keep sector management or manageable aggregates sectors into blocks of some size, perhaps for instance 4K bytes. So some layer of the file system has to deal with that. The file control block is where a file's metadata is stored, so such things as a pointer to the first block of the file, or a table containing the indices of all the pointers to all the blocks in the file, file name, file permissions, creation date, all that metadata. And as you'll see here momentarily, the file system is organized into layers. That's nice from an abstraction and design viewpoint, but of course that gives us then overhead when accessing a file from an application program. So here is the layering, which we'll go over in a moment. I'll simply note that the logical file system knows about files. The basic file system basically just knows about blocks. So the base of the software stack are device drivers, which are the software that interoperate directly across system buses with disk drives. Then on top of it is the basic file system that knows about blocks. So for example, this is the layer at which blocks will be translated into sectors. As mentioned here, the basic file system will also perform block caching and take care of writes of blocks back out to the disk from the cache. The file organization performs the mapping from the logical blocks that a user knows about to the physical blocks that the basic file system knows about, and also manages free space on the device and the allocation algorithms. And then at the top, the logical file system understands the metadata, which of course is kept in blocks within the file system, as well as being able to distinguish between data files and directory files, because directories are just a specialized type of a file. So a particular operating system might make use of multiple file systems. So for instance, Windows has NTFS, as well as FAT32, FAT16, and FAT12, which is used on floppy diskettes, and which you'll get some experience working with. Linux has many file systems. ext3 is what I use, but that's not the most recent version of the ext family. That would be ext4. And then optical devices have their own specialized file systems. Okay, so there are structures on disk that describe the overall file system, as well as individual files within the file system. And then for files that are open, there are in-memory structures, as for instance, a read pointer or a write pointer pointing to the next byte location within the file to be read or written. I'm going to skip this boot control block. Um, the volume control block is what contains information about the overall file system. So in Linux, it's known as the super block, of which there are copies, because since this contains metadata about the entire disk and such things as a pointer to the root directory, if the super block is lost, um, you've probably lost the entire file system. So as you can see here, it contains such information as the total number of blocks, number of free blocks, block size, and then maintenance information for the list of free blocks. So then the file control block contains the metadata for an individual files, typically such things as, let's see, well, in Linux, the file control block is known as the inode, so it wouldn't contain the inode number. Instead, what happens with Linux is that the directory contains the file name, and then the inode number, in essence, pointing from the directory entry to the inode for the file. Here are examples of the sorts of metadata that are kept within the file control block or inode. So within memory, at the overall file system level, there's a mount table which records such things as whether the file system is currently writable or not, the type of the file system, so for example, whether it's an ext3 or an ext4 or NFS for remote file access. And its mount point um, within the system, etc. Then similar data is kept for open files, such things as where the buffers are for cached blocks, etc. So when a file is opened, the file system, the directories within the file system may have to be traversed in order to find the file. For example, if we're using an absolute path name like /user /local /bin /firefox, until we get to the file control block again, or inode for the file, then the file control block information could well be cached within memory, and then if we're reading from the file um, on a per process basis, there's an open file table containing, for example, the offset of the next byte to read from the file. That will also point to a system-wide open file table, so that the system, well, that's where information about the cached data blocks would be kept. The system-wide open file table is also where we would keep a record of how many processes have the file open. Remember, particularly if we're simply reading the file, it's possible for more than one process uh, to have the file open. So there's two types of data. Some data about the file, such as where the blocks are located in memory or on disk, is going to be common to all the processes reading the file, and other information such as the current byte offset is local to each process. The other thing I want to point out here is that at the time file system is mounted, its consistency is checked, and if everything's fine, then it's mounted. Otherwise, there are various tools that can be run or will run automatically to attempt to fix any errors. So given that Linux supports many file system types, such as ext, the file system types for optical devices, and NFS, it's useful to have a layer on top of those, a virtual file system layer, so that application programs are shielded from any details of those particular file system types. So here's a figure illustrating that. All right, so Linux file systems have these four object types. Uh, there's the actual data within the file. So the file, a file's metadata, which is contained within the inode, the superblock, which contains the metadata for the file system as a whole, and then D entry, which is a directory entry. So that's the special file that holds directory information. And remember, what is kept within a single directory entry is the file name and a pointer to the inode. Now, with respect to, so each object is, as said here, each object has a pointer to a function table. You'll be seeing this with the device lab you're working on. So the device has a file operations struct associated with it, which points to the file operations that you're implementing for the device. So a directory entry typically is just a small number of bytes, so some number of directory entries will fit within a file block, but of course if a particular directory contains a lot of files, multiple blocks might be necessary to store all the directory entries for that particular directory. Then we start to run into search problems. The easiest way of organizing a directory is, of course, just a linear list. But searching through that can be time-consuming. So alternatives include hash tables or various sorts of balanced trees. All right, so that finishes this first section on file system implementation. See you next time.